Okay, so by now we've talked a lot about the spine itself. Let's talk about what's holding the spine together. So the spine is a bunch of bones stacked up on top of each other, right? And they're an anchoring point for a number of muscles around the body. And to some extent, some of the tension between those muscle groups will help keep it in alignment. But it's important that those discs don't just go slipping around, right? You have your spinal cord down the middle of it, that thing cannot get pinched. So we have a lot of different reinforcements along the length of the spine to keep everything in place while still affording you a great deal of flexibility and affording you the kind of impact dissipation that you need when you're walking around upright. So what this is composed of is a set or a single intervertebral disc in between the body of each vertebra. See one right here, for example. Color doesn't show up very well on here, but there we are. And a bunch of different ligaments along different parts of the spine that are holding any given part together without just sort of completely shrink wrap encasing the whole thing, which would restrict mobility quite a bit. So we've talked a little bit about our intervertebral discs already. We've talked about how the vertebrae are stacked up on top of each other, but the bodies are really what's bearing all of your weight. The arch of the vertebrae does not bear weight. The spinous processes, the transverse processes, the facets do not bear any weight. It's all through the bodies. You are an upright creature, and so gravity is pulling down on all of those structures on top of each other. And with every step that you take, you have a force that kind of gets transmitted up your body and into your spine. If the bodies of your vertebrae were stacked directly on top of one another, all of that energy would transmit from one directly to the other with no other kind of dispersion mechanism. So those bones are going to get worn down a lot faster than they otherwise would. What we have in between here is the intervertebral disc. In between, that acts like a pillow. So it functions as padding, so those bones are not rubbing directly up against one another. We've talked about how they serve a role in shock absorption, and they provide the spine flexibility. If you want to bend this way, you need to make it so that the corner of this vertebrae and the corner of this vertebrae come closer to one another without leaving open space over here. By putting that squishy pad there, you're able to do that. So we have three main roles. The intervertebral discs are made up of two parts. We have an annulus fibrosus and a nucleus pulposus. Nucleus is in the middle, the annulus fibrosus is the outer part. The annulus fibrosus is a tough connective tissue ring that is, you can think of it sort of just like a tire on a car. It's very, very tough. It does absorb impact, right? It does have a good bit of flexibility, but it's strong. And it's really sort of what's keeping these two bodies of the vertebrae from just collapsing down onto each other. It provides the resistance necessary to keep them from touching, while still providing a little bit of padding. The nucleus pulposus is in the middle, and it is squishy, squishy, squishy. It's almost more like just like a gel kind of in there that's encapsulated so that it doesn't run out. And that nucleus pulposus is what's really going to do the bulk of the shock absorption. It's a low density kind of a material in the middle of this sort of jelly donut. And when that energy gets to that part, it dissipates and is harder to transmit to the surrounding structures. So you can think of the annulus fibrosus as sort of like the pillow, and the nucleus pulposus as your major shock absorber. The integrity of these two structures is really important. When you have an annulus fibrosus that, through wear and tear, develops a hole, the nucleus pulposus, I'm going to change color here just a little bit, even though it's kind of gross color. The nucleus pulposus in here is going to squidge out, right? Because it's just sort of a gel. Your spinal cord is in here. Your spinal nerves are coming out this way. And when the nucleus pulposus herniates into that space, it impinges on that nerve. So the peripheral nerve pain and limited mobility and things like that that you're experiencing when you have a herniated disc is impingement on the spinal nerve at the base of that nerve. And it's because of spilling out kind of your nucleus pulposus. On this slide, you can just see a radiograph of the bodies of the vertebrae stacked up on each other. And we're going to do more radiography in a different video. So there's a body, there's a body, there's a body, for example. It seems like they're a little fractured or maybe not in the best condition. And then your intervertebral discs are in these spaces. So you see one right there, and right there. And if you had a herniated disc, it's not this part that you're seeing very clearly that's going to be what's sort of pushing into the spinal cord. That what you're seeing is the annulus fibrosus. What you would see is really, so you have this dark stuff over here to the side, you would see that sort of impinge a little bit this way maybe. And so all of this filled in here would be more black. It looked like there's sort of a dent in the spinal cord usually. All right. So again, your vertebral bodies are stacked up on top of each other. They are kind of touching, but like by way of that intervertebral disc, they're stacked up on top of each other and in this alignment. The arch of the vertebrae do not bear any weight. You do still have muscles attaching to all of these things and tugging on them all the time, and you want them to stay in place. You also want to make sure that they have a good bit of range of motion, a lot of freedom of movement, but not too much, right? You don't want it to be so loosey-goosey that things could start slipping or falling apart very easily. So you could have ligaments surrounding the whole thing that just completely hugs it like a sleeve. That would work really well to keep everything in place, but it's going to restrict your movement. What you have instead is a bunch of smaller or thinner and often discontinuous ligaments that will keep things held together and keep things in a position where you can avoid things like hyperflexion, hyperextension, slipping around without impinging too much on your freedom of movement. So all of these are pictured here except for the nuchal ligament. That'll be in the next slide. We're going to skip that for now. Let me actually, we're going to ignore this one for now. Sorry, nuchal ligament. Come back to you later. We have the anterior longitudinal ligament shown very nicely on this diagram. And so this is the anterior view, and over here the anterior side. Is over there. The anterior longitudinal ligament is this guy right here. It is a continuous long single ligament, and it runs on the anterior aspect, anterior longitudinal ligament. It runs on the anterior aspect of the bodies of the vertebrae, ALL. Now think about someone bending back and forth, right? You can flex your spine, like along the plane that we're worried about on an anterior posterior basis. You can flex your spine, which is like bending forwards, and you can extend your spine, which is bending backwards. The anterior longitudinal ligament helps keep the bodies of the vertebrae aligned with one another and prevents, which one do you think, hyperflexion or hyperextension? Going too far in which direction? If you said hyperextension, which I know you did, then you're correct. The anterior longitudinal ligament is pretty, these are dense connective tissue kind of sleeves. They're very tendinous. And so when you go to bend backwards, it's only going to have so much stretch, right? So that, in addition to the shape of your spinous processes and things like that, are going to help prevent hyperextension. So prevents hyperextension. hyperextension. If somebody complains about whiplash, that's a problem with your ALL. What happened in that fender bender is the person was driving and then suddenly you stop because of the accident. And because of inertia, you get propelled forward, right? Let's just pretend this is a fairly slow speed thing. The airbag doesn't go off or anything. You get propelled forward. You have a lot of movement or a lot of space to move forward. And then you're going to also go back. And when you go back, when your weight shifts back, it's going to hit your chair or the driver's seat. If you don't have that headrest up, your head doesn't have that backboard and it's just going to keep going. And when you forcibly hyperextend the neck like that, you're going to stretch the anterior longitudinal ligament and potentially tear it a little bit. That causes pain and problems with mobility and generally makes everything in there a little less stable. So this is your whiplash ligament. Your supraspinous ligament, and let me switch colors actually. Red and green, Christmas time. So your supraspinous ligament is only shown on the picture on the right, and that is that one. If the anterior longitudinal ligament prevented hyperextension, these are going to prevent hyperflexion. That's right. So prevents, whoops. Hyperflexion. You also have interspinous ligaments. So this right here is your supraspinous ligament. These aren't real acronyms that people use in the world, by the way. It's just I'm using them because I only have so much space to write. Over here you have an interspinous ligament as well that goes between the spines of the vertebrae, but at sort of a 90-degree angle to the supraspinous ligament. These also help contribute to helping to prevent hyperflexion of the spine. In addition to that, they help sort of keep it so that your spinous processes can only wiggle so far left to right with respect to one another. That's not listed here. It's not one of the major ones that I really need you to learn or worry about. The supraspinous one, though, is just on the tippy tips of those spinous processes. The posterior longitudinal ligament is, let me switch color yet again. Okay, we're going to go blue. The posterior longitudinal ligament, just peeking out here. Now, in case you're disoriented, this whole space in here is the interior of this is the vertebral canal, this open space. So what you're looking back here is the arch of a vertebra and then the arch of the next one. Okay, let me erase some of this so it's not so visually distracting. All right, getting my pen back. So this right here, I didn't get my pen back. Here we are. There we go. Is your posterior longitudinal ligament. And this here would be your posterior longitudinal ligament. This also runs the lengths of the bodies of the vertebra, but on the posterior aspect of the bodies, which is in turn the anterior aspect of the vertebral canal. So posterior to bodies, anterior within vertebral canal. And finally, here we will talk about the ligamentum flavum. And flavum is Latin for yellow or has something to do with yellow, so I'm going to pick yellow. This right here, shown very nicely between the arches, is your ligamentum flavum. You can see that also nicely over here, like that. That's your ligamentum flavum. Clinically, this is relevant for spinal tap reasons. So this is also going to help stabilize and prevent hyperflexion. It will, it is on the posterior within vertebral canal. So it's like if you're thinking about these in sort of colloquial language, it's behind the spinal cord. Posterior longitudinal ligament is in front of the spinal cord. But this spinal tap, think about how you do a spinal tap. You have your patient flexing as much as they possibly can, like full fetal position, holding onto their knees. This is going to spread the spines of the vertebrae apart as far as you possibly can. The intervertebral discs will pinch on the anterior aspect a little bit to allow for this flexion. Your anterior longitudinal ligament will provide no resistance. Your posterior longitudinal ligament and supraspinous ligaments will limit how far that's possible, but you still have a great degree of flexion available there. The ligamentum flavum, when you're advancing that needle, you're going to go through very soft tissue, soft, 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 and then you'll hear a pop. When the needle goes through and makes that popping feeling, it's when you pierce the tough connective tissue of the ligamentum flavum. Once you're past the ligamentum flavum, where are you? You're inside of the vertebral canal, right? Where do they usually do a spinal tap? They usually do it in the lumbar spine, right? Your spinal cord only really goes down to about like L1, L2. At that point, it's tapered off and it's sort of shed all of those nerves. They're all, instead of being in one bundle, they're all kind of very separate from one another. And it's more like having a ponytail in there than one solid rod of nerves. That tail is called the cauda equina. When you puncture through that nuchal, or through the ligamentum flavum, you're going to enter the vertebral canal. You're inside of where the spinal cord should be. But since it's a lot of loose little nerves in there, suspended in fluid, the movement of that fluid when the needle pokes through is going to help move those nerves out of the way so that you don't poke anything. If you did a spinal tap up in, I don't even know how you would do this, but like pretend it's a thing for a second. If you were to do this up in the thoracic spine, you have a solid spinal cord on the other side of that ligamentum flavum that you very, very highly risk piercing, which I'm told is pretty bad. So that's why we do it down there. And this is what goes pop when you do your spinal tap. In this slide, you can see the nuchal ligament. So this is a very limited sort of an area that this covers. And it's going to go all the way from the external occipital, whoops, my pen isn't on. It's going to go all the way from the external occipital protuberance, hug the bottom or the occipital bone down the midline, and it's going to attach to the spinous processes, but sort of encircle them a little bit of your cervical spine. And it goes down as far as C7. That's where it ends. Past that, you're talking about supraspinous ligament. This broad sheet serves the same sort of role as the supraspinous ligament. It prevents hyperflexion and it provides additional support to the head against hyperflexion in this area where the vertebral bodies are so small and there's not quite as much musculature that's preventing anything like that from happening. This also serves as an anchoring point for those as well. Okay, so finally, last slide here, let's talk about the intrinsic muscles of the spine. These muscles are the deepest group of muscles of the back muscles. Almost everything, everything superficial to these are pretty much going to be moving other like upper limb stuff, for example. These are all direct movers of the spine. They enable the spine to move in just about every direction, while also, alongside all of those ligaments, limiting its range of motion into something safe. We have four major groups: the spinotransversalis, the erector spinae, the transversospinalis, and the segmental muscles. So starting with the spinotransversalis, let's get a pen here. And I'm going to use green for these. These are going to be up in near the head and neck, okay? So your splenius capitis is actually really well shown on this diagram right there. And it's going to go all the way up to the head. Splenius refers to bandage and capitis refers to head. The splenius cervicis is almost entirely deep to the splenius capitis. It does not go all the way up to the head. It stops at the cervical spine, and it would ordinarily just like peek out right about here. If your rhomboids are like there and your scapula is there, my very artful drawing, it's just going to peek out right there. Your erector spinae group you should be familiar with from the human anatomy lab. Let's get a different color for this. Let's do like a light blue. Are very, very, very long strappy muscles that run basically the length of the spine. The one closest to the spinous processes is the spinalis muscle. The next one out is the longissimus muscle because it's really freaking long. And then the iliocostalis is the most lateral one. That goes from the ilium and then has like a little finger that reaches out to each of the ribs. So ilio for ilium, costalis for rib. Those are in light blue. All right, so then moving on to the transversospinalis muscles. These are much thinner, wispier muscles than the other ones that we've been talking about so far. Let's pick a different color for those. I'll do like this yellowish sort of a color. All right. The semispinalis muscles run basically the entire length of the spine, and they're going to run from a transverse process of one vertebra up 6 or 7 and insert into the spinous process of a vertebrae superior to it. So these are going to be sort of like twisters of your overall spine, and they're going to be lateral flexors of the spine as well. And they're not super, super close together, so it's going to be sort of a broad thing. Your multifidus does a very similar thing. It's more superficial though, but it goes all the way down from your sacral crest and originates on the sacrum and inserts into the spinous processes. And you can see as we get into the lumbar spine, it does start to originate on the transverse processes of the lumbar spine. Finally, the rotatories. Let's pick a new color for that. All right, so we have purple. All right, those are deep to the multifidus muscles, and they're going to go from the transverse process on one vertebrae to the spinous process, and then it's going to fill in that spot on the sort of the length of the lamina there between the transverse process and the spinous process. It's going to insert into that whole sort of space along the lamina and the spinous process. So this does a very similar thing as the semispinalis muscles and the multifidus muscles. They all kind of do a twisty thing. These segmental muscles, the next group here, I'm running low on colors that are good. I'll just have to use black, I guess. These are going to run usually just from like one area to like the next, for lack of a better term. So the levators costorum run from any given rib. So there's 12 of them total, and then on upwards there too. And these insert on the superior surfaces of the rib, or sorry, these insert into the transverse processes above them. So this goes up to there, to there, to there, to there. So you see they only really go like one vertebrae's worth or rib's worth up at a time. The interspinalis muscles and intertransversarii are not very visible here because the spine is basically entirely covered up. Interspinalis muscles go between the spinous processes of 2 adjacent vertebrae, and intertransversarii go between the transverse processes of 2 adjacent vertebrae as well.